Hello, bonjour, it's Laura here. In this video, I'm going to show you how to write a net ionic equation. So I've got a question written here. Write the complete ionic and net ionic equations for the following balanced equation. And then I've got an equation written underneath. Okay, so the magic word here is balanced. Always look for that in your question. If it doesn't say that it's balanced, you need to first make sure that your equation is balanced. It's very important that we're always starting with a balanced equation. For all kinds of chemistry questions, you always want to start with a balanced equation. All right, so we've got our complete molecular formula written here. So all of these compounds, they're written as molecules. Even though they're aqueous. So we've got the calcium chloride here. Notice that's aqueous. That means it actually is not a molecule when it's in that beaker. It is actually in water. It's calcium chloride in water, and it's been disassociated into its ions. That's what the aqueous means. So the first step here is we'll write our complete ionic equation. And when we do that, we're going to show what's really in the beaker when these two solutions are mixed. Okay, we're going to show that we've got a bunch of ions floating around, not a bunch of molecules. All right, so we've got from the calcium chloride, we're going to have calcium floating around. Now, we need to make sure that we know the charge of calcium. We always write the charges in our ionic equations. So calcium is going to have a 2+ charge, and you know that from the periodic table. Calcium's in group 2. Now, how many calciums are floating around? There would be 3 from the calcium, and again, that would be aqueous. So you always have to put that aqueous behind the ion. Now, with the chloride, chloride's going to be floating around. The charge on chloride is -1. How many chlorides would be floating around if this molecule disassociated? Well, in every one of those molecules, there's 2 chlorides. And chloride, when it's an ion, it's not Cl2. It's just Cl. So that means that there's always going to be, when this calcium chloride breaks up, there's going to be 2 chlorides. And we actually have 3 of these calcium chlorides in this balanced equation. So that means we'd have 3 times 2. So that means we'd have 6 chlorides altogether floating around. Okay, so a lot of students make the mistake of writing 3Cl2, but that's not right. There's actually, Cl does not float around as a Cl2, it floats around as just Cl. And there's 6 of them. Okay, so now let's look at the next one, the sodium phosphate. So we've got sodium, it's floating around, and it's got a +1 charge. Now, sodium's the same as chloride. It's not going to float around as Na3. It's going to float around as just Na, single by itself. That means that there's 3 times 2 sodiums floating around when sodium phosphate breaks up into ions. Okay, and then what about the phosphate? So the phosphate is interesting. It's a polyatomic ion. That means, remember, polyatomic ions stay together. So the PO4, that stays together. It's not going to break apart. That's the ion, PO4 together. And it's got a 3- charge. So I can look at my table of polyatomic ions and I'll see PO4 has a 3- charge. Now, how many would be floating around? So you look at the coefficient, and there's 2 of them in this balanced equation, so there should be 2 PO4s. Because there's only 1 PO4 in the compound, but there's 2 of the compounds. All right. So there's lots of stuff, lots of ions floating around in that beaker. Now we'll look at the calcium phosphate here. Notice the calcium phosphate is a solid. So is that going to break up into ions? No, like the S there tells us that even though it's in a beaker of water, it's solid. Okay, so don't change that, and you don't have to break this up into ions because it's not broken up into ions. It's actually a solid. So this is actually nice. We don't have to break this all up into ions. I think we'd run out of space. So calcium phosphate is a solid, so you write that S for the solid state, and it doesn't, that's all we have to do with that one. Now let's do the sodium chloride. So we've got sodium, and again we know it's a +1 charge, and there'd be 6 of them because there's 6 of those compounds, and so when it's broken up there would be 6 NAs floating around. Now with the chloride, we know that it's got a -1 charge, and same thing, there'd be 6 of them floating around. So this is something else students sometimes do, so be careful. Notice there's a 6 in front of the sodium chloride, so sometimes people will write 6 in front of the sodium, but they'll forget to write the 6 in front of the chloride too. But when 6 sodium chlorides break up, it's gonna have 6 of the sodium, 6 of the chloride. So be careful with that. Make sure that you use the coefficient for every part of that compound. All right, so that's the complete ionic equation, and you can see that it is really quite messy, quite a lot of stuff to look at here, and it's almost so confusing that it's not valuable for somebody to even look at. So that's why we have the net ionic equation. And I actually find that it's nice to write the complete ionic equation, but the net ionic equation is what you want to end up with in the end. Now, what we do with this net ionic equation is eliminate all of the mess, all of the extra stuff that's in our complete ionic equation. And so what we're going to do is look for ions on the left side or the reactant side, and look for the same ion on the product side. And if we have ions that are floating around on the reactant and the product side, we know that they're not really part of the actual reaction that is happening. So for example, I'll start with the Cl. We've got Cl in our product side. Notice we also have it in our reaction side, or reactant side. So that means chloride was floating around in the beaker before and after the reaction. So that means that it didn't take part in the reaction. So I'm just going to cross that out. Is there anything else here we could cross out? So I notice we've got sodium in our reactant side, also in our product side. So that means at the beginning of the reaction in the beaker, sodium's floating around, the reaction happens, sodium's still floating around. That means it didn't take part in the reaction. These two things are called spectator ions, and you'll hear that in class as well. So these are spectator ions. They're kind of in the beaker watching what's going on, but they're not actually taking part. So we're just going to take them out of the equation. They just cause it to look messy. Now what we do is we write just what's left over. So we've got 3 calcium ions. We've got, so I wrote that, we've got 2 of the phosphate ions, and we already figured out the charge, and we already figured out the coefficient, so it's pretty easy for us to write this out. And then we've got our solid, so the calcium phosphate, and make sure you write the S for the state. Okay, so that's our net ionic equation. So you can see that it's not as messy. It's clearer to read. We see that really what's happening is we've got 3 of the calcium ions. They're combining with 2 of the phosphate ions. And when they do, they form a solid that's not soluble in the beaker of water. It actually would form a solid. It would probably sink to the bottom, and we'd be able to see that that is different than all of the rest of the water that's in the solution that's in the beaker. Okay, so that's how you write the net ionic equation. I recommend that you write the complete ionic equation first, and when you do that, really concentrate on getting your charges right in your ions and getting the coefficients in front of the ions correct. Then when you get to writing the net ionic equation, it's really easy. You've already got your coefficients, you've already got your charges. All you have to do is cross out your spectator ions and write it all out. Okay, so that's how you do that type of problem. Well done, Miigwech.